Hello, hardworking subscribers, viewers. If you're new to my channel, welcome. I'm Miga, and today we will be talking about isomers. It's one of those important topics that come up easily on the first or second exam of your first organic chemistry class, and it's easy to get confused because the professor usually tend to go fast on this material, expecting you to go home and review. So let's go and try to make a very clear show every difference between the different type of isomers. So first we're going to talk about the two main type, two group of isomers, right? And then we will be able to talk about the different type of isomer in each group. Okay, so let's first talk about those two groups: constitutional isomers and stereoisomers. The most important skill, I believe, is to differentiate whether you're dealing with a constitutional isomers or a stereoisomers. What's the difference between them? Well, in both cases, we will have the same molecular formula. But in the case of the constitutional isomers, we will have different name, different physical and chemical property, and different connectivity of the atom. Meanwhile, in the stereoisomers, we will have also the same molecular formula, but the connectivity will be the same. Most of the time, they have the same physical and chemical property, but the spatial arrangement is different. What do I mean by that? First, let's take a look at constitutional isomers. Like I said before, constitutional isomers have the same molecular formula. For example, let's say you see on your exam C3H6, right? C3H6, there's many ways to write C3H6, right? And one way, I will present it here with a double bond, right? And another way, let's say if it's like it has a cyclic type of connection, right? Connectivity. So we can see that based on those two ways of drawing, the name will be different, right? And when the name are different, when we're dealing with two different compounds that are arranged in different way, most of the time they behave differently. Their physical and chemical property are different. So what would be the name of this compound on the left? We would have propylene. The name will be propylene for this one. And on the right, the name will be cyclopropane. Wait, let me remove this. Cyclopropane. If you're on the exam, you're not sure, try to name them. If you see any difference in the name, while you're trying to figure it out, for example, let's say if you are given those two compounds, you see this. We know that because we have a double bond, there should be an in. And here we have no double bond. That would be an ane, right? We know that, oh, okay, that's different name. Here we're dealing with constitutional isomers. You don't even need to worry about whether or not it's stereoisomers, right? Because stereoisomers have the same name. And I'm going to show you where the difference is later on. But remember, it's not only the connectivity only that can be different, right? In constitutional isomers. We can have a difference in functional group. What I mean by functional group, for example, here, this compound here has an OH, which is an alcohol group. And here, in this compound on the right, the oxygen is in the middle. That's an ether, two different groups. So we know that the name will be different, right? We can see that the molecular formula is the same in both cases. We can have the same functional group, but the location of those functional group like the functional group is at different location on the compound. Let me show you what I mean. For example, in this case, yes, both compound have both molecules have 3 carbon, both molecules have a bromine. However, the substituent here, the bromine group, the bromide is on carbon 2, but the bromine is on carbon 1 for this compound. So we know because the location are different, even if we might have propane, but the number for the bromo will be on different, right? For example, this one, if we had to name it, we will have two bromo, two bromopropane, as opposed to this one is one bromopropane. Okay, so that's how you know if the name, by the way, when I'm saying the name, it's not only this, the number matters too for for naming. If numbers are different, then the name is different. Thus, we have different compound. Okay, based on what I just, all those examples I gave you, now you can understand this little chart that says that we have the same molecular formula, but different name, different connectivity, etc. Now, let's go ahead and talk about stereoisomers. In the case of stereoisomers, like I said before, they have the same molecular formula, generally have the same physical and chemical property, and same connectivity, but the only thing that differs is the spatial arrangement. Let me show you what I mean by that. Let's take a look at this first type of stereoisomers, the cis and trans. For example, if we're dealing with an alkene, right, a compound with a double bond, look at how here we have the same type of connectivity. For example, this compound here has 1, 2, 3, 4 carbon on the left. So 1, 2, 3, 4 carbon on the right, right? We have 2 hydrogen group on both compound and 2 metal group on both compound. So the same type of connectivity, right? The same atoms are the same atom or element are on this compound, right? However, the only thing that differs is the 3D spatial arrangement. You see how here in this case, the CH3s, the metal group are on the same side, and on the other example here, the metal group are on like opposite side, right? So here, so for naming, we'll see that both have the same molecular formula, right? C4H8, but on the left, we'll see that for the naming, this one, but 2-butene doesn't change. The only thing that are different is those little words in the front of the name, cis and trans. Cis mean that those groups are on the same side, and trans mean that those metal group are on opposite side. And it's not only cis trans, there's other way like S, etc. that will be that are useful to indicate the spatial arrangement of certain atom, right? But this is just one type of stereoisomers that shows you the difference in spatial arrangement, but with the same name. When I'm saying name, this part where that tells you the number of carbon, the type of group, functional group in it, and the location of the functional group, that part should be the same. If you're on an exam and you're realizing that the naming is the same, then you're dealing with stereoisomers. What type will be after you first determine if you're dealing with stereoisomers or constitutional isomers. Now that you understand what I mean by different in spatial arrangement, let's get into the different type of stereoisomers. There are 2 types of stereoisomers. We have configurational stereoisomers and conformational isomers, also called conformers, rotamers. Okay, so I'd already talked about cis and trans. Cis and trans is a type of configurational isomers, but we also have enantiomers and we also have diastereomers. What is the difference between those two? Well, configurational isomers are restricted in rotation, like you can't interconvert them. For example, remember when I was showing you the cis and trans? Let's go back here. The cis and trans, you cannot simply rotate this bond, okay? You cannot do this. Let me put in purple. You cannot rotate this bond to enter convert it into this. That's not gonna happen because the double bond is limiting the movement of that bond. Like the atom are stuck in that position. That's why it's not you can't enter convert them. But in the case of conformational isomers, you will be able to rotate the molecule, to rotate a pi, a sigma bond, to interconvert it, and we'll talk about it soon. But now, since we already talked about cis and trans, let's continue our discussion about the configurational isomers that have restricted rotation, like you cannot interconvert them between molecules, right? So since we already talked about cis and trans, now we will talk about the other type of stereoisomers, which are the enantiomers. Enantiomers are mirror image of one another, and they are non-superimposable. For that, I would like to quickly give you an example with my hands. If you look at my hands, we can agree that they look like mirror image of one another, right? It's like one is looking at the other one through mirror. So that's what we mean by mirror image. However, we can agree that they are not superimposable. I can't just merge my hand and then you can't convert your left hand into your right hand, right? Your left hand into your right hand. It's just not gonna happen. If you have a glove that fits the left hand, you cannot just place it on the right hand. That's not gonna happen. So that's what we mean that they are not superimposable. Each hand is unique. Each hand fits in its own gloves, non-superimposable. So now that you understand what I mean by mirror image but non-superimposable, let's look at these two molecules. Usually, when you have a mirror image compound, a lot of time, in enantiomers, some of them will have chiral centers, and usually it's easy to determine if two compounds are enantiomers. For example, if we have a chiral center, if you don't know what chiral center is, I would encourage you to watch my quick video about how to determine R and S. But I can quickly say it again. A chiral center, for example, in this case here, this carbon that I'm pointing here, is a carbon that have 4 different groups attached to it. For example, here we have one group that is different from that group, which is different from this group. Oh, that's a little messy. And of course, with an hydrogen on the back. But you know what? Maybe I should make another quick video about that. But for now, let me say it, thinking that you already know what I mean, right? If you have a chiral center, after determining if your chiral center is S or O, for example, in that case, we only have one chiral center, usually the enantiomer should be the complete opposite, okay? For example, in this case here, after determining if we have an O or S configuration for this compound, I found that this center is an S one. So after I determined the chiral center, the configuration for this chiral center, and I saw it was O. And indeed, they are perfect opposite. That's how I knew that I'm dealing with enantiomers. So remember, enantiomer is a type of stereoisomers. That means they should have the same molecular formula, and you can see that the molecular formula is the same. They have the same type of group on it, right? And which means that the name itself should be the same, which is alpha methyl benzyl benzene ethanamine. This shouldn't change. However, we have something in the front of the name that determine that tell us what type of spatial arrangement is in the molecule, and that is a sign that we're dealing with a stereoisomers, right? But here, guys, we only have one chiral center, right? And I said that we need complete opposite so that we can have enantiomers. Let's look at another compound that has more than one chiral center. After drawing those two and determining, I realized that we have 2 chiral center on each molecule. And I saw that on the first one, molecule on the left, we had two S Chaos center, but on the right we have two because those Chaos center are perfect opposite. I know that I'm dealing with enantiomers. I should probably put an S here. But what if they are not complete opposite? What if we have SS and here we have, for example, RS or SR? They are not complete opposite. How would you call it? Do you know the name? If you guess diastereomers, then yes, you guessed right. Indeed, we call that a diastereomers. Diastereomers are not mirror image and they are not superimposable. They are not mirror image because we can see that they are not, the Chaos center are not perfect opposite. For example, here, look at this molecule, we have SS, but in that case, we have one that is of course, the perfect opposite of the first Chaos center, but it's the same as the second Chaos center. Not perfect opposite, then we are dealing with diastereomers. I hope that you are still following me so far. If we zoom out, so far we've talked about three types of configurational or geometrical stereoisomers, cis-trans, enantiomers, and diastereomers. Now let's go on the other side and let's talk about conformational stereoisomers. They are isomers that can be interconverted by rotation. What does that mean? Again, if you're familiar with the Newman projection, I quickly draw one molecule here, and I would like to make a quick demonstration of this compound. I cleaned this up a little so that you can follow what I'm about to tell you, but if you're already familiar with the Newman projection, I believe you know where I'm gonna go with this. But first, let me show a quick demonstration where I build this molecule and you will see what I mean by we can rotate, we can interconvert between structure by rotation. Here is the exact molecule that I showed you a few seconds ago. We have 1, 2, 3, and 4 carbon, and this will be our fourth carbon, and that one will be our back carbon, so that we can draw the Newman projection. And we will rotate this bond here. So you see how I'm doing some rotation, all right? And I'm going to an eclipse where we can see that there's a lot of steric hindrance, right? Between those two groups. Of course, we know there will be a lot of ion energy is required to even achieve this conformation. And then we can again rotate it and rotate it from staggered to eclipse to gauche, etc. So that's what they mean by rotamers, okay? So quickly, now that we're back on our page, here, let me quickly draw my eyes looking at this structure. All right, let's not forget our hydrogen in the front, and we have two more hydrogen pointing out in the back, right? And we're gonna, if we realize that we can rotate this bond in the middle so that we can have different structure. We can have this one, we can have many different one actually. For example, one of the rotamers could be this one here, right? Remember, on the first one, the CH3 were away from one another. They were anti, but we can have this structure where we have a gauche conformation where the CH3s are close to each other. Okay, so that's what they call rotamers. Also, another form of rotamers is with chair flipping, when we can have some group on a chair conformation that some group can be, some substituent can be in the actual position, but only by flipping it, we can switch it to an equatorial position. So that you can see how simple it is, but most of the time, the professor isn't going to test you on that because it's very simple. If we go back to our little map here, most of the time the question will be about differentiating whether you're dealing with constitutional isomers or stereoisomers. And if yes, are you talking about diastereomers, enantiomers, or cis-trans? Yes, that's usually that's where the focus is. But I would like to do some practice problem on the next video so that we get more familiar with solving such question, okay? But that's what I have for now on clarifying the differences of isomers, okay? So remember, keep on studying, keep practicing until you know and understand the material so that we can move on to the next topic, okay? You got this, and see you on the next video.